Brought to you by the Astro Youth House chapter from STEM Arts Lab, Space on Earth is a student-led podcast that inspires listeners who are curious about space to explore the wonders of the universe through the voices of young thinkers, creators, and dreamers.
Each episode blends personal curiosity with scientific discovery, from the mysterious depths of black holes to the practical impacts of space on Earth, like GPS, climate science, and medicine.
Hosted by STEM Arts students from Taos, New Mexico, this podcast draws connections between space, art, and science, how these things all impact us here on Earth, and their meaning to humanity.
You'll hear raw, insightful conversations about topics like light pollution, the overview effect, lunar exploration, and the societal impact of the space race.
Whether you're into exoplanets, dark energy, or just stargazing from your backyard, Space on Earth makes space personal, accessible, and inspiring. We believe that space isn't just for astronauts and scientists, it's for everyone.
Join us on this adventure as we explore the cosmos from Earth, one story at a time.
Special thanks to the Lore Foundation for helping launch this podcast.
Hi everybody, welcome back to another episode. I'm Taylor.
I'm Hattie.
And today we're here to talk to you guys about stars. We're going to be talking about what is a star, and we're going to be walking you through the life cycle of one. HattieRose, do you want to start us out with a definition of a star and kind of an idea of what it is?
Okay, so what is a star? A star is an astronomical object that emits light and heat from nuclear reactions happening at its core. These reactions fuse hydrogen into helium, and it releases a lot of energy. They're made out of hydrogen and helium. The hydrogen is about 70%, while the helium is about 28% on average. They're basically just these massive spheres of plasma. Taylor, do you want to tell us a little bit about spectroscopy?
Of course. So you brought up what stars are made out of, and you're talking about all these different elements and materials. But first, there's the question of how do we find out something like that? Obviously, we can't go up to a star's surface and collect a sample. So we find other scientific ways of getting this data. And one way is that when light passes through a star's atmosphere or anything inside of that star, so certain wavelengths of that light get absorbed, which tells us which elements are in the gas. So we can get a lot of information about what that star is made out of just from seeing that from whatever light is absorbed. And we can also see if it's passing through a planet's atmosphere of what's in the atmosphere of that planet. So like I was saying, we see a color from stars, but that's not from the spectroscopy. That's not the actual color of the star. However, the actual color of a star in space gives us a lot of information too. HattieRose, you want to go into that a bit?
So there is a lot of stars, for example, Beetlejuice, which we'll talk a little bit more about later, which appears red to the eye, but it's a lot, like thousands of degrees hotter than fire, which is interesting. And there's a ton of different colors that you can see in stars, depending on the temperature, and they can go up pretty high in Celsius, like blue, yellow, white, orange, red. And red is actually on the lower side, while blue is a bit more on the higher side. You can look at stars like our sun, for example, which is yellow, and that's approximately like 5,000 Celsius around that point. I think it can be a little bit more as well. And that's a star type G. There's a bunch of different classifications for types of stars. There's like O-type stars and M-type stars and a lot more.
So there's all these different classifications where you're talking about is if you picture it on a graph, imagine your y-axis is talking about, okay, how much light is this star emitting? And on the bottom is how hot it is. And so what we see is there's that correlation there. And you have really, really bright blue stars that are super hot. And so those are going to be your O-type stars. Our star is a G-type star, so it's not as hot. So that's where that yellow color comes from. And other stars that are of similar like heat and light as our star are going to be the same color.
Exactly. So there's also different types of stars. There's giant and supergiant stars, there's dwarf stars, there's exotic remnants. You can look at like red dwarfs, which is an M type, and these are like some of the coolest and most common stars in our universe, in the universe. And they can live up to trillions of years, and they're really hard to see with the naked eye. There's also white dwarfs, which are pretty hot but faint. They have a really faint glow from residual heat. And there's also black dwarfs, which is a hypothetical endpoint for white dwarfs after cooling. There isn't any yet, but research shows that we might see that in the future. As for giant and supergiant stars, there's red giants, and then there's blue giants and supergiants. And the red giants are kind of like the sun. They expand after the core hydrogen is used up. So they have cooler outer layers, which makes them appear more on the red or orange side. And then blue giants and supergiants are really big. They're really young, and they're very luminous, and they're pretty short-lived, and they commonly end in a supernova.
So you brought up white dwarfs, and I kind of want to go on that for a second. So a quick bit of information and context. White dwarfs are dead stars. So that is what stars like our sun is going to become someday. And you brought up hypothetical black dwarfs. And so that's it kind of puts into perspective of how we can only in our lifetime study and see a small portion of a star's life cycle. Stars, they live over billions of years, and we aren't around to see all of that happen. But we can use a lot of data and science to figure out where they'll go. And we can look at stars that are very far away to kind of get a glimpse into the past. We can look at stars similar mass and heat to ours to know what'll happen to our star. So I think that that's a really interesting kind of way to think about how we use the small amount of time and information that we're given to find out really big and amazing discoveries. How did you have anything to add to that?
I can add a little bit before we move on, which is I think it's also interesting how you can really identify the lifespan and the end stage and the mass and the burn rate based off of color. For example, a star that's blue, has a very high mass. The burn rate is very, very fast. And instead of billions or trillions of years, it usually only lives for about millions of years, which is still a lot. But in contrast to the other ones, it's not as much. And the end stage, it usually goes from a supernova to a neutron star or a black hole. And I also quickly want to touch on the exotic stars like neutron stars and black holes. So neutron stars are basically the dense remains of a supernova, so they're very tiny. They also spin really rapidly and can emit beams of radiation called pulsars. Black holes are formed from the collapse of very, very massive stars, and the gravity is so intense that not even light escapes. I know that black holes are very popular, even like a lot of people know about them, even if they're not as informed about space. So I feel like that's very fascinating to talk about.
So you brought up black holes. And so basically what a black hole is when you get a bunch of mass and it gets super condensed. We don't know a lot about black holes because we can't really collect data from them, because once something gets close enough to a black hole, we can't get any of that back. But we do know a lot of things about black holes from their surroundings. And so that was another thing where with black holes, we couldn't look at them and see them and say, oh, I see something in this photo, in this data that looks like a black hole. Because they're absorbing light, we can't see anything when we're reading information. But what people were seeing is that so gravity, especially as strong as black holes, disrupts light. What astronomers were seeing around the time that black holes were discovered were points where they would be seeing 4 stars instead of 1. And they looked at that and they figured out, okay, what could this be? And they realized it could be a really strong gravitational disruption. And so that's kind of how we figured out black holes. And black holes come from very high mass stars because there needs to be a lot of mass condensed into a small area in order for it to be a black hole. And anything with mass could potentially be small enough to create a black hole. And the size that it has to be in order to have that happen is called a Schwarzschild radius. So that's always a fun thing to look into is like how big would like a person have to be a black hole. So you can look into that. Schwarzschild radiuses are about like how condensed mass has to be a black hole. So that's a direction that stars can go in when they die. And recently, we had a moment in astronomy where we were seeing a star that we thought was going to go supernova. And it's a star that most of you have probably seen if any of you have looked at Orion and the night sky. And that's the Beetlejuice star. So this star would be located if you're looking at the constellation of Orion on his shoulder. It's a very bright and noticeable star in the sky. And so when astronomers started seeing long periods of dimming and brightening with this star, it was exciting about this is that if Betelgeuse had gone supernova, it would have been visible from Earth and it would have been an amazing stargazing experience. But that's not what we're figuring out is more likely. Upon more research, it looks like it's not actually dying, but that there's two stars instead of one.
So that's called binary stars, and it's kind of just like when two stars orbit each other. Betelgeuse has a dimming event that went on 2019 to 2020, which is really interesting. I know that you know a lot about binary stars and dimming stars, if you want to expand on that.
Yeah, so what the data that we were seeing with Betelgeuse is that it was having that it would have a moment where it was a lot dimmer and then would start getting brighter when we looked at it and when we looked at it through telescopes. And so that would be over a really long period of time, and those periods got longer. And so that's what kind of started having scientists look into it and focus on it a bit more. And the theory is that instead of it being one star, there's two orbiting around each other in a binary system.
It's really interesting that when we talk about binary stars because about 60% of stars are binaries, and our sun actually isn't a binary, which is a little bit odd. So there's also different types of brightness variations in dimming and variable stars. Like there's eclipsing binaries and intrinsic variable stars. So eclipsing binaries are binary star systems where one star periodically passes in front of the other and causes pretty predictable dimming from Earth's perspective. And this is really important for determining stellar mass, radius, and orbit. Variable stars can also help us calculate distances, which is really, really helpful when you're looking at or studying stars. Intrinsic variable stars have brightness changes due to internal processes like pulsations, eruptions, or rotation. And there's a couple different types, like Mira variables, which is long period pulsating red giants, Cepheid variables. Those are actually used to measure distance across the universe. This is an intrinsic variable star. And then the extrinsic variable stars, their brightness varies due to external causes, in contrast to internal processes like eclipses or star spots. There's also a ton of stars that we could look at, such as Betelgeuse, which had the dimming event, which I previously mentioned. Between October 2019 and February 2020, it lost 60% of its brightness and caused widespread excitement and speculation that it might go supernova, which you just mentioned. I think that's really fascinating, though. There's also the Demon Star, which is in the constellation Perseus, which is 90 light years away. That has an eclipsing binary system, and it's composed of a B-type main sequence star and a cooler companion. And these orbit each other every 2.87 days, producing a sharp dip in brightness.
I think that that's super cool. I think that's a lot of really great information. So with stars, we've been talking a lot about supernovas, and we brought up black holes a bit. And so that all ties back to how and when a star dies. So what happens with stars is that they're running on fuel, and that's what keeps them hot and producing light. And eventually this fuel runs out. So if you look in the case of our star, we have a very low mass star. And so what our sun is going to do is that once it starts running out of fuel, it fuses hydrogen to helium. When it runs out of hydrogen, it starts to fuse the helium, which is way hotter, so then the star expands. And it'll end up going past some of the inner planets. So our sun will actually envelop planets like Mercury and Venus and even Earth. Luckily, none of us will be around when that happens because that's in a really long time. Like we were saying, that stars have billions of years in their lifetime. And so after that happens, the star looks really red from the outside. And that's because what you're seeing on the outside of the star is so far away from the source of heat on the inside that it looks dimmer and colder.
So, after low mass stars like the sun inflate, it turns into a red giant and the helium fusion begins. So, the hydrogen in the core is gone, but the hydrogen in the outer layers still fuse in a shell. So, the core contracts and heats up until it can fuse helium into carbon and oxygen. And then usually there's a white dwarf left behind, but also things happen in between that, which is the star becomes unstable after the helium runs out and the outer layers start to float away into space, forming a glowing shell of or gas, which is also known as like a planetary nebula. And then it turns into a white dwarf. So there's no fusion, just a lot of leftover heat, and then it cools down for billions of years and eventually turns into a theoretical black dwarf. And then for high mass stars like Beetlejuice, it can inflate into a red supergiant. And the core fuses elements like hydrogen into helium, into carbon, oxygen, neon, silicon, and then iron. And this builds pretty layered shells, kind of like an onion. And then the core collapses because the iron can't fuse to release energy. And once the iron builds up in the core, fusion stops and gravity collapses in the core in less than a second. And that's when a supernova happens and it explodes. And the outer layers are blown off into a massive explosion. And the remaining core becomes a neutron star if it has 1.4 to 3 solar masses. But if it has more than that, then it becomes a black hole. This is really important because stars can get back to the universe when they explode, so that they can eject materials like carbon, oxygen, iron, sometimes even gold, and this is what helps form new stars, planets, and possibly life. I think this is also really fascinating because we are made from atoms that were once inside these stars that inflated, exploded, and died millions, billions of years ago.
And there's a really great quote about that from Carl Sagan, where he says that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made from star stuff. And so this is a really great quote, and it really emphasizes what you were talking about, Hattie, is that all the material that is distributed and dispersed in these supernovas, it reforms and it creates things, and it creates planets and new stars and life on those planets. And so that's where we come from. So that it's a really cool way to bring back all of these things. So a fun little way to look at it is that calcium in your bones from like really massive star deaths. And when you're breathing in, you're breathing oxygen that comes from red giants, and DNA is carbon nitrogen from earlier generations of stars. And so it really brings together this image of how everything is so connected on such a long scale of time, which I think is really amazing. So that's what we want to cover for today. Thank you guys so much for listening. HattieRose, do you have any extra things to add?
Yeah, really quickly, I just wanted to say that this is really important to remember because it kind of just reminds us that we are a part of the universe, even if it feels so far away or we feel so small in comparison. There's also so much to discover, but we can talk more about that in another episode. I hope you guys enjoyed listening today. Anything else you want to add, Taylor, before we wrap up?
Not really. Thank you, everybody at home, for listening and supporting us. Like always, if there's anything that you want to hear about in the future or anything that you're curious about, let us know. Send us an email, and we'll be able to go do some research and tell you guys everything we know. Thank you so much for listening and supporting. I'm Taylor.
I'm Hattie.
Have a great weekend.
Thank you. Bye.